Hello everyone. In this lecture we will be looking at the boundary conditions for the electric and magnetic fields that exist at the interface between different media. So before we start again, just a recap of the Maxwell's equations. This is the first Maxwell's equations, which is the Gauss law, which essentially says that the divergence of the electric displacement is equal to the charge density. Then the second Maxwell's equations, it is the divergence of B is equal to 0. So this there's no named as such. There's no law which is ascribed to this particular equation. We can just derive this equation from the fact that there are no magnetic monopoles. The third Maxwell's equations is the Faraday's law, which says that the curl of the electric field is equal to the negative of the time derivative of the magnetic field. And the last one is the Ampere-Maxwell's law, which relates the curl of the magnetic intensity with the time derivative of the electric displacement, and this is related to the current density. So we'll be using two of these Maxwell's equations for the boundary conditions for the normal component, and the other two Maxwell's equations for the boundary conditions for the tangential components of the electric and magnetic fields. So let us proceed now. So the boundary conditions at the interface of different media. So suppose I consider two different media which are denoted as 1 and 2. So this is one medium, which we call as medium 1, and this is another medium which we call as medium 2. Okay, so in the first medium, the electric field is E1, magnetic field is B1, electric displacement is D1, and the magnetic intensity is H1. Similarly, in the second medium is E2, B2, D2, and H2. And let's say there is some kind of a surface charge distribution at the interface. There could be some kind of a surface charge distribution, which is sigma. So what we do is these fields are shown as given here, and then what we do is we want to find out the boundary conditions for the perpendicular field components. So when I say perpendicular field components, this is what I mean. So let's say this is the interface, and then perpendicular. So we could have, let's say, electric field this way. We could have electric field display. Okay, so when I say perpendicular component, we are talking about the component which is perpendicular to the interface. Okay, so this is the perpendicular component, that's what we are talking about. So which we can write as, so this is, let's say, the electric field. Then this perpendicular component, we could just write this as E perpendicular. We could write it like this. Okay, so we want to find out the perpendicular field components. So for this purpose, what you do is we consider a pillbox surface. So this kind of a surface that we see over here, it is a pillbox surface because it resembles the boxes where people used to store medical pills in the olden days. So it looks like it's basically a cylindrical surface. So we have a pillbox surface whose volume is V. So this pillbox has got a volume. The volume of this pillbox is V. And it is bounded, the surface of this, the surface which bounds this. So this surface includes the top surface, the bottom surface, and the side surfaces. So this total surface is S. Okay, so S is the total surface which binds this particular volume V. So now over here we will define the area of the top and the bottom of the pillbox. So this top surface that we see over here, this top surface, that is, we're talking about this surface, and of course which is also going to be the bottom surface. So this top surface, it has got an area, and that area will refer to this as delta A. This is the area of the top surface. Then the epsilon is the length of the pillbox. Let me just shift this. Oops. The surface. Okay, so let's say epsilon is the length of this pillbox. So this length of the pillbox. Okay, S is the total surface. So epsilon is the length of the pillbox. So then what is the total volume which is enclosed by the pillbox? The total volume will simply be the surface area times the length. That is going to give us the total volume which is enclosed by this pillbox. So now what you do is, we will again use go back to the Maxwell's equations. The Maxwell's equations 1 and 2, one homogeneous and one inhomogeneous equation. The first Maxwell's, the Gauss law and the absence of magnetic poles. So this is the inhomogeneous equation and this is a homogeneous Maxwell equation. We will use these Maxwell's equations over here. So the first equation, equation number 1 and equation number 2. Now what I'm going to do is, we are going to take the volume integral of these two equations over the entire pillbox. So this equation, I'll take a volume integral over this entire pillbox, and same way over here also we take a volume integral of this over the entire pillbox. So I take the volume integral of divergence of D over this entire pillbox. So now what is d tau? D tau is a volume element. Okay, so d tau is a volume element within this pillbox. Okay, so this is what we take. So now this is a good time for you to recall what is known as the divergence theorem. So what is the divergence theorem? The divergence theorem basically says this. So suppose I have some volume, okay, it could be any arbitrary volume. Let's say I have some volume, and this volume is bounded by some surface. So we have some volume which is having some surface as the boundary. So the surface which bounds this is, let's say, S. Then let us say there is a vector field which is defined. Okay, let's say some vector field A which is defined inside this volume. Then if I take the divergence of A, and this quantity, of course, is going to be a scalar function, because when you take divergence it becomes a scalar. And if I take this integral, the volume integral over this entire volume, this will be equal to, now what we have to do is we have to look at the surface. Okay, consider the surface here. Okay, let's say you take a small surface element. Okay, so this small surface element, let's say, is dA. Okay, this small surface element is dA, and this will have a normal vector which is n cap. Then this volume element is equal to, evaluating the volume integral of the divergence of A is the same as evaluating the surface integral of A over this entire boundary surface. Okay, over the entire boundary surface. So in other words, the volume integration of the divergence is equal to the flux, the total flux of this vector field through this entire surface. Okay, so this is your divergence, the so-called divergence theorem. Okay, so we can now apply the divergence theorem. You can see here we can apply the divergence theorem on the left hand side, because here also is the same thing. We are taking the divergence of a vector field over this entire finite volume. So that means we will have to essentially take the closed, of course, I had forgotten to write over here, because the surface is closed, so it's a closed surface integral. So this is a closed surface, the flux of this D over this entire surface. Now over here I will just I have introduced this new vector called as n cap prime. Okay, and what is n cap? Let me tell you the difference here. First of all, what is n cap? Okay, so let's say this is the interface, and on this interface, in the direction which is perpendicular to the interface, okay, the direction which is perpendicular to the interface, there is a unit vector. Okay, there is a unit vector. That unit vector is what we call as n cap. So over here, this is n cap. So n cap is a unit vector which is pointing perpendicular to the interface. Okay, so now what is this n cap prime? Okay, so here we'll have to make a distinction. So let me draw a pillbox surface here. So let's say this is a pillbox surface. So we have one face, and this is the side surface. This is the side surface, and this is the other surface. Okay, backward face. Now what is this n cap? Because you are taking the integration over the entire surface, so imagine a surface element on the side surface, right? So let's say this is a surface element on the side surface. So there is going to be a unit vector which is going to be pointing outward. There is going to be a unit vector pointing outward. Likewise, if I take another surface element, let's say somewhere over here, if I take another surface element somewhere over here, then the surface vector, the surface vector, the area vector is going to be pointing in this direction. So now if I take surface element over here on this face, then in this case this is the normal vector to this surface at this point. Okay, so this surface, the normal direction with respect to the surface, these are your n cap primes. Okay, so this is the difference between this n cap and this n cap prime. Okay, so this is the n cap prime, and then on the right hand side what we are doing is we are taking the integration of rho d tau. Now we know that rho d tau is nothing but when you integrate the volume charge density with respect to volume, it gives you the total charge. So what is the total charge that is contained inside this cylinder, inside this pill lock? So the total charge contained inside, there's no reason that you have to use rho to calculate this. You can as well use sigma, because sigma into area is also going to give it a total charge. So sigma times this area, that is going to give us this total charge. So sigma into delta A, that's going to give us the total area. So the total charge. So now in a similar way, if you integrate this one, okay, so the volume integration of the divergence of B, which is equal to 0 because the right hand side is 0, and then applying the divergence theorem, we have this. So we have these two equations. Then what we do is, let us say if I try to, because I'm trying to make this this surface as small as possible. So if I want to make the surface as small as possible, that means I have to set this epsilon, I have to make it tend towards 0. Then both the surfaces will tend towards the interface itself. Okay, so we'd like to make this epsilon tend towards 0. We have to see what will happen to these two integrals in the limit as epsilon tends to 0. So as epsilon tends to 0, the side surface does not contribute to the left hand side above, which makes sense because as epsilon becomes smaller and smaller, this side surface is going to shrink. So the only surface which does not shrink, which is going to remain steady, is going to be the top surface and the bottom surface. The side surface is going to shrink. So the side surface, the contribution of the side surface to this integral and to this integral, that is going to become 0. So when that happens, so all I need to do is evaluate this dot product at the upper surface, that is at this surface, and evaluate the dot product at the lower surface. And when I do that and take into account the directions, we get this d2 on the medium to d2 dot n cap into dA. So now you can note here, when we are talking the top surface or the bottom surface, top surface n cap prime is going to become equal to n cap. You can just see here, if you take the top surface, n cap prime will become equal to n cap, and if you take the bottom surface, n cap prime is going to become equal to minus n cap. So that's why you get a minus sign over here, and this is equal to delta sigma delta A. So delta A is going to get cancelled everywhere, and this is what we'll get. So d2 minus d1 dot n cap equal to sigma. Let's call this equation number A. In a similar way over here, so same thing, only the top and the bottom surface contribute. So b2 dot n cap into delta A minus b1 dot n cap into delta A, which is equal to 0, which gives us b2 minus b1 dot n cap is equal to 0. Let's call this equation number B. So equation number A, what does it imply? It basically tells us this, that the normal component, because you see, how do you get the normal component? If you again look here, when I say normal component, how do you get the normal component? So let's say I have the electric field. E is the electric field, right? E is the electric field. So what is the normal component? What is the normal component of the electric field? The normal component of the electric field is this E perpendicular. And how do you get this E perpendicular? All I need to do is take the dot product of E with n cap, right? So when you take the dot product of E with n cap, that is going to give us the projection of E along the n cap direction, which is nothing but the normal component. So what this equation tells us is, what I'm doing here is d2 dot n cap, that is the normal component of d2, and d1 dot n cap, that is the normal component of d1. So that means this left hand side, what it is giving is, it is giving the difference between the normal components. So the difference between the normal components, it is a non-zero quantity. That means the normal component becomes discontinuous. That is, if you go from one medium to another medium, and if you observe the normal component is going to undergo a change at the interface. So there is a discontinuity which exists for the normal component. So the normal component is discontinuous across an interface, and the discontinuity in the normal component of this displacement is equal to the value of sigma at that point. So if whatever is the surface charge density at a point, that surface charge density will be numerically equal to the difference to the discontinuity in the electric displacement at that point. So that's what equation number 1 is. Equation number A, that's what it tells us. Equation number B, what does it say? Very simple, because the right hand side is 0, that means the normal component of the magnetic field B, that there is no change, right? Because normal component in second medium minus normal component in the first medium, which is equal to 0, that means normal component in both the media is going to remain the same. Normal component in medium 1 is equal to normal component in medium 2. So that means the normal component of the magnetic field, it remains continuous. It is not discontinuous, it is continuous across an interface. One way to understand is in this way. I have a medium. This is the interface, and let's say sigma is the surface charge density. So this is medium 1 and this is medium 2. So this is the normal component of electric displacement in the first medium. This is the normal component of the displacement in the electric displacement in the second medium. So what this equation number A tells us, what equation number A, what it is essentially telling us is that this minus this is equal to this. That's why you can see the difference here. So this is I have deliberately drawn this vector as having a larger length compared to this, so that you can see that there is a difference. So as you go from one medium to another medium, there is going to be a discontinuity. So the different discontinuity, that is this quantity, this component minus this component is equal to this. But there is no such thing in case of the magnetic field. Okay, there is no discontinuity in the magnetic field. So both the vectors, both the components of the magnetic field vector in the normal direction, they are going to remain the same. So that's about the normal component of the boundary conditions for the normal components of the field, the electric and the magnetic fields. Now let's look at the tangential component. Let's look at the tangential components. So boundary conditions for the tangential field components. So what we will do is we'll again consider the same scenario, but this time instead of a pillbox surface, earlier we had taken a pillbox surface, but now what we will do is we will take a closed contour. Okay, we will take a closed contour starting here, going all the way here, and then piercing into the surface, going on to the other side and coming back here. So we are going to take a very simple rectangular closed contour. Okay, a rectangular closed contour. So this rectangular closed contour is C, and the surface that it binds. Okay, so this is going to have a surface. Okay, so this closed contour is going to enclose a surface. That surface we will call it as S prime. So now you see there are again two directions here. One direction is the normal direction, and this one is the tangential direction, because this tangential direction is perpendicular, is along the surface, is parallel to the surface, and this is perpendicular to the surface. So let's say I have this to be the medium, this is the medium, and then I consider a field, electric or magnetic field. Let's say this is the field. Okay, let's take the example of the electric field again here. Then, or rather let me do it this way, this is the tangential direction. Okay, this is the tangential direction. So the unit vector along this direction is t cap, and the electric field or the magnetic field will have a component along this t cap direction. So this component, okay, this component of the electric field, which is parallel to the tangential unit vector, this one we call it as E parallel. Okay, as opposed to in the previous case, this is a normal direction, we call it as E perpendicular or B perpendicular. Here it becomes E parallel. Okay, so now this T is the tangential direction. Okay, so we choose a contour which is perpendicular to the T as well as perpendicular to the surface itself, and this contour has got this contour is called as C, and the area that it encloses is S, and this contour is rectangular in shape. So now let's just define certain quantities. So we will have a delta L here, a length of this. Okay, so length of this is, we are basically talking about this length, and the width of this, or vice versa, we call this as epsilon. Okay, So here the delta L is the length of the contour and epsilon is the width of the contour. So then again we pick up the Maxwell's equations 3 and 4. This is Maxwell's equation 3 and this is Maxwell's equation 4. This is a homogeneous equation. 3 is a homogeneous equation and 4 is an inhomogeneous equation. So now again, just like earlier, what we will do is, earlier we had taken a volume integral. Okay, we had taken a volume integral here. Now for equations 1 and 2. So here instead of a volume integral, we will take surface integrals. Over which surface? Oops. We will take surface integral over which surface? Over this surface S prime. So let's take a surface integral over S prime for the first one. Okay, so curl of E, take the surface integral of curl of E. This is equal to minus the surface integral of dou B by dou T. Okay, and over here dA prime is a surface element on this surface S prime. Now what do we use here? Is there any previously there was the divergence theorem which came to our rescue. Here what kind of a theorem do we use? Here we use what is called as the Stokes theorem. Just to help you recap, what is Stokes theorem? Stokes theorem basically says that suppose I have some contour. Okay, suppose I have some contour C, and this contour C, it bounds some surface S. Okay, so let's say I want to find out what is the there is some let's say there is some vector field which is defined in this region. Okay, there's some vector field. Let's say we call this as vector field as A. Okay, now this vector field, we could find out the curl, right? At this point, at any point, we could find out the curl of this vector field. So let's say this turns out, because a curl is also a vector field, so this is the basically the curl of the vector field. Okay, this is a curl of the vector field. So now what we do is we take a small area element. Okay, we take a small area element which is dA, and this area element, there will be a normal vector, the unit vector which is normal to this n cap. Now what you do is we find out what is the surface integral. What is the surface integral of this curl of A? So in other words, we try to integrate this curl of A dot n cap into dA. So we are basically trying to find out the flux. Okay, in other words, we are trying to find out the flux of the curl of A. So what is this equal to? For that, what we have to do is, again, we need not evaluate this curl of A at each and every point inside the interior. All we can do is we can just take the boundary. At the boundary we will have, let's say, this is a length element which is dl. Okay, and at this point, at the boundary point, we find out what is this same vector field, what is the value of the vector field at the boundary. Then what you do is we take the line integral, the closed line integral, okay, over the entire contour. So A dot dl. So we can replace the flux of the curl of a vector field with the line integral of the vector field itself over the boundary of the boundary contour which contains that surface over which we are taking the flux. Okay, so we can apply this over here. So curl of E, we are taking the flux of the curl of E. So this can be replaced with E dot dl taken over the contour C. So E dot dl taken over the contour C, and the right hand side will remain the same. Only difference that I have made here is I have introduced, like previously, I have introduced this n cap prime. Instead of calling as n cap, I'll call it as n cap prime. N cap prime is a unit vector, okay, which is perpendicular to the surface at each and every point. So this dA, I'm just writing it as n cap prime into the magnitude of dA. So now what is going to happen is this. Okay, now there could be some contribution from this side. Okay, from this side as well as this side. If you look at the expression that I have written over here, we are only considering the contributions due to these two sides. We are only considering the contributions due to this side and this side, because I am multiplying with delta L. We are not considering these two contributions. The reason is again same as before, is as epsilon tends to 0. As epsilon tends to 0, these two contributions will become negligible. So we only need to consider the contributions due to this E2 dot into delta L and E1 minus delta L. Okay, so now what about this vector t cap cross n cap? You can work this out for yourself. You can see for yourself, t cap is in this direction, n cap in this direction. So t cap cross n cap, the direction, if you just do a cross, if you do apply the right hand rule for finding the cross product, t cap cross n cap, the direction will be this way. This will be the direction of t cap cross n cap, and which is going to be along this length, okay, and minus means along this length. Okay, so that's why I have replaced that, just to, because we only have these two directions at hand. We have only n cap and t cap, so that's why we can use n cap and t cap to obtain these directions. Okay, so that's why you get this. So the right hand side remains just the same as before. Similarly, for the second equation, curl of h is equal to the surface integral of this quantity. Okay, so we apply the Stokes theorem here and we get this h dot dl. Same reason, because as epsilon tends to 0, only the contribution due to the upper surface, this segment and the lower segment, only that is going to remain. So t cap, and this one is again it is going to give you this direction. So we have this expression which is written like this. Okay, so now another implication of this epsilon tending towards 0. Okay, as epsilon tends towards 0, another implication is that this quantity is also going to tend to 0. Okay, as epsilon tends to 0. Why is that so? Because you can see this is a surface integral, right? This is a surface integral. As epsilon tends to 0, this surface area is going to vanish. As epsilon becomes vanishingly small, yeah, you could have some length, but area is nothing but length into breadth, right? So length could be finite, but if the breadth tends towards 0, then the area itself is going to become vanishingly small. So this surface integral is going to tend towards 0. Okay, so that's the reason for this, is the area tends to 0. So as a result, we will have this one. Okay, t cap cross n cap dot e2 minus e1 is equal to 0. Then in a similar way, okay, so I could write it this way: t cap cross n cap dot e2 minus e1 is equal to 0. So now I could also alternately write this as n cap cross e2 minus e1 dot, which is equal to 0. Okay, you can work this out for yourself. This dot this vector dot this one is equal to 0. This is the same as this vector cross with this, because n cap is anyway t cap cross n cap, it is perpendicular to both t cap and n cap, right? And so I can equivalently write this as a cross product. Okay, now again, as epsilon tends to 0, unlike in this case where there was a single surface integral and this surface integral tends towards 0, here the same thing is not going to happen. The surface integral is not going to tend towards 0, even though the area is tending towards 0. The reason for that is there is a current density, right? And current, it can flow on through over a surface also. In your Griffiths, you would have probably come across this surface current density, which is K, right? So this J, because what is this J dot n cap into dA? You are taking this current density into area. Current density into area is going to give us electric current. So current density into area is the same as surface current into length, right? Surface current into length. So essentially what you're trying to do is, what this is going to give us is this term is going to be 0. This surface integral term is going to be 0, but what is going to be left behind is j dot n cap prime into dA. That is going to give us some kind of a current. So it's possible that some kind of a current is flowing through this one. So some kind of a current, which we refer to as K, the surface current, that is going to definitely flow. So we could have a current which is flowing like this, right? So this current is going to flow through this loop. So as a result, definitely this component, this contribution by J to this surface integral, this is definitely going to be non-zero. So that is going to be some surface current, and this, because the total dimensions of this quantity should be equal to current. So therefore this must be equal to some K, some surface current K into the length. Okay, so here length will get cancelled. So we have again this expression t cap cross n cap dot h2 minus h1 is equal to K, and so this can be written as n cross h2 minus h1 equal to K. So equation number C, what does this imply? equation number C implies that the tangential component, because see here n is the normal component, so n dot, if I do n dot, it will give me the normal component, but if I do n cross, it will give me the tangential component. Okay, so n cross e2 minus e1, this is going to give us the tangential component, and this tangential component is, on this side we have 0, that means this is the null vector, that means the tangential components, they are equal on either side. The tangential component of the electric field are equal on either side. So the tangential component of electric field is continuous across an interface. Equation number D, what does this imply? It says that again in a similar way, the tangential component of H is not equal to, the difference in the tangential component of H is not equal to 0, which means there is a discontinuity. There is a discontinuity in H across the interface, and this discontinuity in H is equal to K. Whatever is the surface current at that point is equal to K. So we can express this in this way, diagrammatically we can understand it this way, because there has to be a the tangential component of the electric field is continuous. So electric field, this is the tangential component, E parallel, so E1 and E2, you see both the vectors, they are of the same length, so there is no change. Okay, it remains the same when you go from one medium to another medium, but the magnetic intensity, there is a change. This length and this length, they are not the same, so there is a change, and this difference is equal to the surface current through at that point. Okay, so we have had this as the idea. Okay, previously this is the same idea for the normal component, this was the boundary conditions. For the tangential component, this was the boundary conditions. So what we can do is we can just combine these two diagrams and we can just express this. For simplicity, I have just shown electric and magnetic fields. So what is going to happen is, for electric fields, the tangential component remains continuous from one medium to another medium, but the normal component remains discontinuous. So as a result, if in one medium this is the tangential component and this is the normal component, in another medium the tangential component remains the same, but the normal component will be different. So consequently, if this is the electric field in one medium, in another medium, this is how the electric field is going to look like. But the magnetic field, the normal component remains the same. So from one medium to another medium, the normal component is discontinuous, but the tangential component is the normal component is continuous, but the tangential component is discontinuous. Okay, and this discontinuity in the tangential component depends on K. So as a result, in this case, when you combine these two components, you will get the total magnetic field to be this. In this medium, this is how the total magnetic field is going to look like. So this brings me to an end of this lesson on the boundary conditions for the normal and the tangential field components. Thank you.